We are the last presentation, the last thing between you and the drinks, so I'm sure you pay a lot of attention to us. My name is Torben, I'm from Techno-Lab, this is Mathieu from médialab. You can say your names.
Yeah, so I'm Michele from Landscape Design. Agata from Landscape Design too.
I'm Wafa.
Anthropology.
And I'm Marie from Ethos Lab at ITU.
Okay, so we have far too many slides and far too many things to say, so we just try to rush through it in a good way. One way to talk about this is to tell you that ambiguous nodes can be many things. So roughly speaking, it's about when we have network graphs. Are there then nodes that they are difficult to place within perhaps one cluster, or do they have connection to several clusters, and how do we manage these things? But we have really worked a lot from a particular data set, which is about obesity research that we know from a previous data sprint. So we have constantly asked about what would ambiguous nodes be in relation to this particular data set. The way we have, our interest in ambiguous nodes is very much to say, can these nodes be used to challenge some smooth stories, some stories that are too easy to tell or too clear? Can we use these ambiguous nodes to tell us something different or to challenge the smooth stories? I've been allowed to talk for 1 minute about obesity research, so I'm going to do that now. In obesity research, there is one very smooth story, which is if you ask actors who are involved in the field of obesity research, they would say that obesity is a national epidemic. For this reason, when we research obesity, we have to look at what make particular populations fat. And the answer to that is to look at the entirety of all sorts of causal factors, such as the food we eat, the amount of exercise we do, our genes, the environment, the physical environment, all sorts, our eating habits, the whole thing. So the field of obesity research believes that it's trying to build one big comprehensive model about everything, the entire obesogenic environment, the whole thing that makes a particular population fat. So that's one very smooth story about how obesity research is coming together. This is story one. So story two, which is slightly less neat, is a story we developed in a data sprint 2 years ago. We harvested 500 articles about obesity research and tried to look at how are they actually treating the notion of environment in these articles. And we discovered that there were actually 5 different notions of environment going on in obesity research. So with that story, we challenged the neat story that everything's coming together, and instead we developed another story which could perhaps look like the one on the right here, that there are, instead of just one nice model, everything in obesity is related to each other. Then we pointed to 5 different notions of obesogenic environments. And what we have been doing in the past 3 days, is that we have worked on moving beyond this sort of 5-item neat story about obesity to look at what happens with the nodes that perhaps are floating in between these neat clusters, and are there any other interesting connections we could look at so that we could challenge this story, which is neat, less neat than that original story, but still quite neat. So that's what we have been working on. And we've been doing that in 2 ways. The first one is to look at what we call ambiguous modularity nodes. Those are the nodes that are sort of on the edge between 2 clusters. And if you run the modularity algorithm, as a lot of you know, then you will sometimes find that this node is in one cluster and sometimes in another. How can we understand that, and how can we trace that? And the other thing we've been looking at, that's what we call long external links. That's the kinds of nodes that we can find that are firmly located within one cluster, but then despite that they have connections to other clusters that are far away. So what do those connections mean? So those edges mean. Those are the 2 kinds of ambiguities that we have been trying to locate and trying to explore qualitatively in the past days. Yeah?
So this corpus, this network, is a network of words related together when they appear in the same documents, and it has been produced by software named Cortex, and it's important to mention that because there is a lot of filtering involved in the process. So some minor edges have been removed in order to show nicer clusters, if you will. So we worked with the traditional output of Cortex that looks like many other outputs of Cortex other people may have used here. And we've done two different kind of things. So the first project is about looking at the nodes that fall in different modularity clusters depending on what happens when you run the modularity. And then the second sub-project look at the connections. So this is all of the same data set, okay, the one you had seen before as a network on the right. So let's start with the first example. So we have this network that we run into Gephi, and then we run modularity clustering, which is a way to detect communities. And it tells you which node belongs to which community. So some of the nodes are in the same community, some are not in the same community. So it's just a random number, arbitrary number, labeling each node, and we call that a modularity class, if you want. It's not a deterministic algorithm. It means that even on the same data set, if you run it twice, you don't have exactly the same result. You may see it as an effect of an approximation. So what we've done first is we've played with a parameter, almost the only parameter of that algorithm, which is called resolution. It allows you to have more or less clusters. Okay. So we've done 2 runs with the resolution 1, 2 runs with the 2, 3, 4, 5. So you have different avatars of different resolutions in 10 runs of this algorithm. And then we've done something, a lot of manual work, in order to match the clusters, because you have an arbitrary number, but sort of intuitively, the cluster which is on the left, which is labeled as modularity class number 1 on the first run, may be the number 4 on the second run, but it's mostly the same. So then we relabel them so that we have like A, B, C, D, like relevant clusters, and we used the empirical description of the cluster. That's why we can name them when it works. So we have institutional environment, built environment, food environment, family, and body. So what you see here is each row on the image on the right. Maybe I will just switch to the next slide. Each row is a node. Okay. So each column, you have 10 columns. Each column is a run of the modularity. And so on the top left, the previous one is better. But here you have, like, for instance, the first node was always in the cluster institutional environment. But some of the nodes were not always in the same cluster. So one of the weird things here is that we have sometimes an additional cluster, because in the beginning we have more clusters. So the black one was not labeled empirically, but then it disappeared. So you have a bunch of nodes here who were selected as in another additional clusters. Oops, what did I do? And you see that here, some of these nodes here, which were in the family cluster, jump to the institutional cluster, sorry, again. They jump back and forth, okay? You have also some nodes jumping from family to built environment. I mean, it's pretty clear now, I believe, how you can read this visualization. So, first of all, most of the nodes stay in the same cluster. That's why you have big color blocks. But some of the nodes jump back and forth. So these nodes do not belong as strongly to their cluster as other nodes. So ambiguity is not all the same. Ambiguity is sometimes, some nodes are more ambiguous than others. Next experiment. Running more of the same modularity settings. So 5 times with the same resolution on 4 different resolutions. So if we do that, we can visualize the clusters on the map. So you have the same map that was labeled by Torben earlier, with the name of the clusters here on the same colors. And you can see that, so on the left, I don't want to touch the touchpad anymore. On the left, you have a big bunch of nodes which always belong to bodily environment. And they are circled by 5 times a red line. It means that 5 times they were in that cluster. But as you can see here, you have a smaller bunch of nodes which are labeled by twice by the red line and 3 times by the pink line. It means that 3 times they fell into family environment. This is only for resolution 1, for the setting 1. So most of the nodes, as we've seen before, belong quite firmly to their cluster, but some of them switch from one cluster to another. So it was expected in a way, but some of these nodes that are here between built environment and food environment jumped from one cluster to another once. Of course, they are in between, so it makes sense. So if you look at what happens with the different resolutions, so this is resolution 1, this is number 2, I will just pass them as a series. Resolution 2, resolution 3, resolution 4, and just 4. So let me go back, also so that you can see the evolution. So let me just give a small focus. So in the beginning, let's compare this one and this one. This one is resolution 2. On the bottom, you see that there is a cluster that is pretty scattered. So it's a pretty complicated situation, more complicated than we might expect. So for instance, all these nodes here, they were disputed between 3 different clusters. I don't know if the colors are very clear, but sometimes they were with the pink, sometimes with the blue, and sometimes with the yellow. And the yellow is not even so close geographically in this image. But still, there are some links, so the modularity is sensitive to these links. And how can I say that? The topological position of these nodes is more complicated than it looks like if you just look at the image. And if you have a higher resolution, you might see that entire clusters become disputed. So here, we have a huge bunch of nodes which were sometimes a separate cluster in pink, and sometimes completely merged with the blue cluster. So it tells us something else. It's not only a question of the nodes that are the more in between are the more ambiguous, but sometimes completely full clusters might end up on one side or another depending on the randomness of modularity. So if we look at the nodes that are disputed the more, we can see that there are certain kinds of words. I don't know if we have, if we want to dig into that.
I can just say very briefly, as I have together with some colleagues just written an article where we build on modularity and tell a clear story about 5 different types of visualizing environment. And this is a violent and shocking tool to be faced with, because this potentially rips up the neat divisions that we have made, and it forces you to look at the nodes that are ambiguously positioned between clusters. And I've been supposed to look at these and try to think hard if does that really challenge our neat story. I think it doesn't fundamentally challenge our neat story. And I can tell you this was a horrible moment to have to look into this to be faced with all the ambiguity and uncertainty about this clustering. So this is a rough tool to challenge yourself when you have sort of developed first your fairly neat stories about the clustering of data.
Yeah, so we've tried to scale up a little bit by developing a script that would not require to code the clusters manually so that they match from one run to another run. So we've done that. Of course, we can't color the clusters anymore because we don't know anymore which is which, but we can still visualize where do the divides fall when we separate the nodes in different bunches. And then we can also compute a metric for the ambiguity of the nodes. So here it's the same network, and basically we run completely different resolutions, so not 1, 2, 3, 4, but like 0.1, 1, and 10. And then I don't know if it's very clear, but sometimes you have a big line. It means that on our 10 different runs, it's always the divide always fall on the same place. And when you have a thin line, it means that just one or twice it was separated there, but the rest of the time it was not separated there. And so we can look at which nodes fall inside the same category or not inside the same category to compute a metric, an ambiguous metric. And here you have the measure projected as a surface. So you see that depending on the resolution you set for modularity, it's not always the same areas that are ambiguous. So the solid areas are sort of often the same, but the vulnerable, the ambiguous areas are not always the same. So it's like a weird frequency thing where your algorithm is sometimes blind to some ambiguity and sees another kind of ambiguity depending on the setting you use. So you cannot just run modularity 10 times with the same settings and see where it's ambiguous. I mean, you would have to run it on a various range of resolution. Just to finish on that topic, if we just run the same script on the network less filtered by cortex, which is the one on the right, and you can see something which is, we have much more modules and much more ambiguities, but still two areas, one on the top and one on the bottom right, are still completely unambiguous. This means that there is a solid thing inside modularity. If you run it many times, you have a bunch of nodes that always fall in the same modules. But if you run it only once, you don't know which is which is sort of an issue. Yeah, so just a very basic word about the difficulty to build that metric, because you don't know which cluster is which. The only thing you can look at is if every pair of nodes fall in the same category or not. So you measure the variation of if each pair of nodes is either always together or never together, or sometimes yes and sometimes no. And then you have to collapse this metric, which is on the node pair level, to a metric on the node level. So that's how we build this metric. Well, I've sort of given elements of interpretation about that already. So I think I'm just going to jump to the next section.
Okay.
So for you, Torben.
Thank you. So this is the second of our, we did several experiments, but this is sort of the second branch, which is about nodes that are firmly located within one cluster, but still have long external links to other clusters. So what does that kind of ambiguity mean? What we did here, or rather what Mathieu did here, was to develop a script that could detect the longest edges between clusters, and then find all those edges, and then we'll try to analyze these connections. What do they mean? And visually speaking, it is like this. There is the base map of the original 5 clusters, and then with this script we can locate all the long connections, for instance, between these two clusters. One cluster called the family environment, the idea that the family habits and so on is what makes people fat, and the bodily environment, which is a completely different idea, which is that the deposition of fat tissue takes place in an environment of other organs within a body. So it depends on the genes and on physiology and so on. And then when I look qualitatively at all these edges between these two clusters, it struck me that despite there are very different kinds of research going on in these clusters, the family environment would typically be big national surveys, and the bodily environment would typically be clinical studies. Then despite that, there is sort of a shared policy arena across these two clusters. It's all about regulating family health issues and mothering, especially how to feed infants and to take care of infants and unborn children. So there is all these connections. When I read them again, suggest to me that there is sort of a particular kind of policy, family policy, health policy going on between these clusters that is quite different from the kinds of policies that are being performed in the other kinds of clusters. So this again suggests to me that even though these clusters can be thought of as separate, there's also something that unites them. And if we had to make sort of a super category, which could be policy areas, this would be a policy area of its own. So that's the kind of experiment or finding that can challenge the initial smooth story that we have produced earlier. And I think in the interest of time, I won't go too much into the other examples, but here is also a series of connections between family environment and food environment. No, I won't go into that. I'll just show you the last one here, which is a lot of connections between family environment and institutional environment. And what that suggests when reading into the specific data is that a lot of the family environment research is about what goes on within the family home, but it's actually quite closely connected to what goes on for the same kids in their school life. So what kind of school diets do they get, and what kind of exercise opportunities do they have in school? So these kinds of connections remind us that family life, or the family as an environment around the obesity of children, or an environment that affects the obesity of children, is intimately connected to schooling and school institutions. So again, this is something that sort of, if not directly challenges, then at least adds quality or adds interesting questions to the kind of initial categorization into clusters that we have done in previous research. Okay, so with that, I'll just say thank you both to you, the audience, and also to the group. It's been a great pleasure to work with you. I've had a lot of fun. Yeah, so now it's time for questions or comments.
Thank you, Torben.